Hi everyone, this is Dr. Manjula Sri, professor in the Department of Electronics and Instrumentation Engineering. In the series of lectures of Computer Organization Design, in this lecture I would be discussing the basic computer control unit and what is the instruction execution cycle of the basic computer. The control unit of any processor is like it translates the machine instruction whichever is fetched from the memory into signals in order to perform the micro operations in order to implement that instruction. So what exactly it does is fetches an instruction from the memory which is in terms of zeros and ones and generates the appropriate control signals in order to implement the micro operations in order to fulfill the instruction. And the control units are implemented in two different ways. One is said to be the hardwired control and the other is said to be the microprogrammed control. In hardware control unit, it is made up of sequential and combinational circuits and the control signals will be generated by these hardware units. Whereas in case of microprogrammed control unit, so a control memory is used which will be having all the micro programs that will be activating the required control signals. So the control signals will be generated by executing a micro program in the control memory. So it is exclusive for the control unit, that microprogrammed control unit. So we will be considering the hardwired implementation of the control unit for the basic computer. Basic computer is with a limited hardware and limited functions. So it is easy to implement hardware implementation with the basic computer. So as we go with the microprogrammed control unit, so there are certain limitations as well as advantages. Hardwired control unit once designed cannot be changed, whereas microprogrammed control unit can be changes can be amended. So as per the changes required, we can change the microprogram in the memory. That is the advantage. And coming to the speed, hardwired control is faster compared to the microprogrammed control unit. This diagram shows the control unit of the basic computer. It is implemented with hardware control. As we know, like the instruction is available, it will be brought when it is fetched from memory. The instruction is kept in the instruction register. So how is this instruction fetched is usually program counter is meant for holding the address of the instruction that is to be executed next. So once an instruction is completed, execution is completed, then the program counter contents will be placed in address register in order to fetch the next instruction. And once it is done, then the read operation from the address what AR is holding will be brought into instruction register. So it will be done in two steps. In the first step, program counter contents will be placed in the address register. In the second step, memory read with the contents of the address register will be done and the contents, it is nothing but the instruction. So that instruction will be placed in the instruction register. So these two cannot be executed parallelly. They should be done one after the other. Then only the right instruction will be fetched. So in order to provide timing, there should be a timing signal generated. So which will be generating clock pulses. So usually a sequence counter, a 4-bit sequence counter is used for the basic counter which can generate 4-bit counts. So 2 to the power of 4 counts will come. So it is given to a 4 to 16 decoder so that 16 timing signals can be generated once it is starting. And I don't mean that all the instructions will be taking 16 clock pulses. It may take 3 clocks, 1 clock, maybe 4 clocks, 5 clocks, not more than that for the basic computer. So the entire instruction execution will be taking maybe 3 clock pulses, 4 clock pulses or 5 clock pulses, only up to that. Once that is complete, again it will be starting from 0. So we'll be resetting the sequence counter so that again it starts generating T0, T1, T2 and so on. So if you look at the block diagram, from the instruction register, the contents will be given to the combinational control logic, where it will be decoding and will be generating the appropriate control signals. So the opcode part is given to a 3 to 8 decoder. So this is opcode part. This is opcode part. It will be decoding into uh, 8 signals, 8 different signals. So first 7 will be meant for the memory reference instruction. 7th one will be for the register reference or input output instructions. So whenever it is generating, the output of the decoder generates D0 to D7. So all the memory reference instructions, each one will be associated with D0, D1, D2 and so on up to 7. Up to 7 signals, D0 to D6. D7 will be associated with the memory reference as well as the register reference instructions. And at the same time, timing unit will be generating the timing signals. It is nothing but formed with a sequence counter together with a 4 to 16 decoder. So 16 signals will be generated, 16 timing signals. It is nothing but clocks, timing clocks, clock cycles, right? So each sub operation is defined for one clock. Almost one clock, one sub operation can be executed. So in that way it is timed. And the 15th bit, I mean I15, which is addressing mode, whether it is 0 or 1, based on that will also be going to the control logic, which will generate a control signal whether it has to go for a second fetch or not. So in case of indirect memory operation, it has to go for a second fetch. In direct memory, it does only one fetch for the instruction, for the operand. Okay, so that's about the block diagram. And if you look at the timing signals, these are all the timing signals. So timing signals are generated by the 4-bit sequence counter and the 4 by 16 decoder. So for every clock, if you look at this, so for every clock, it will be generating a next count. So starting count will be, it's a 4-bit sequence counter. So first count will be 4 zeros. So for the next clock, it will generate 0001. So like that, for every clock, it will be incremented and will be reaching the 16th clock, right? But not all are used. Maybe 4 to 5 will be used for the basic computer, or maybe less than that also. And these are given to the decoder and they will be generating T0 to T5 signals. So for every count, it will be generating 1. For 000, T0 will be active, remaining all will be inactive. So for next count T0001, T1 will be active, remaining all will be zeros. So what happens is only that clock will be active, remaining all will be zeros. So this diagram is nothing but showing the same thing. Clock is a signal which has been given to the sequence counter. For every count, one timing signal, one timing clock will be active. See, T0 will be active only during T0. So for the next clock, T1 will be active. It goes high and again comes back. Similarly, like it will be generating T0, T1, T3 and so on. And as I said, like up to T4, this instruction, one example is taken like, if an instruction is taking 4 clock pulses, T0, T1, T2, T3, T4, 5 clock pulses. So after that it will start again, it will reset. At the end of the last clock pulse, a sub operation is to clear the sequence counter. So it will start again, start generating T0, T1 and so on, which will be used for the next instruction. Okay. So in this example, like assume at a time T4 sequence counter is cleared to 0 if the decoder output D3 is active. So the condition is that if decoder output D3, what is D3? The control signal meant for one of the memory reference instruction D3, right? So in order to execute that instruction, it should happen at during T4, it has to stop and clear the sequence counter. So for that, the condition is that both should be active. When D3 is active as well as T4 is active, the sequence counter should be cleared. The activity that how sequence counter is cleared is we will be sending zeros to the sequence counter, initiating with the zeros. So that should happen at this clock. That is what the meaning of this uh, operation. So when D3, T4 are 1, if both are 1, then only this will be 1. At that time, this instruction will be, or this sub instruction will be, or micro operation will be executed. That is the meaning of how the timing signals are associated. So together D3 and T4, we'll be calling this as the control signal. When the control signal is 1, then this operation will be executed. So all the sub operations will be implemented in the same way. So every sub operation or micro operation will be associated with a control signal. So that is nothing but whatever is to be generated by the control unit. So when it is generating that control signal, then only the instruction will be executed. That is how it happens. So let us see how it is done. Another thing to be considered for each and to see how each and every instruction is executed. We call the process what the basic computer does in order to execute an instruction, we'll be calling as a instruction cycle. As I said, like once one instruction is executed, it has to execute the next instruction. Right. So we'll be having the instructions in sequence, instruction 1, 2, 3, and so on. So once this is executed, it has to execute the next one. So that is why the operations that are performed for every instruction will be calling as one cycle. So the instruction cycle. So the entire instruction cycle is divided into different subsections. And of course, they also depend on what is the type of instruction or different for different instructions. Okay, so most every instruction has to be fetched and decoded, that is for sure, and execution should also happen based on whether it is using a memory reference or not for the data. It will be again performing a fetch, and if it is an indirect addressing mode, then it will be performing 2 more fetches for the data. So otherwise, fetch, decode, and execute are common for each and every instruction. These 3 should be mandatory for all the instructions. So in short, I would say like in the basic computer, a machine instruction is executed in 3 to 4 steps. Okay, the 4 steps are fetch, decode, reading the operand, and executing. Reading the operand will refer only in case of memory reference instructions. In case of register reference instructions, they will be available in the register and directly the execution takes place. Right? So in short, we call fetch, decode, execute. In short, it is fetch, decode, execute are the 3 steps in the execution, in the instruction cycle. Okay, but because also there are memory reference instructions and most of the operations are operated or being done as a memory references, we also include a data fetch or an operand fetch. So if you look at the first operation is fetching an instruction from memory. Fetching is nothing but reading from memory. So reading from memory into the appropriate register is nothing but the fetch. Then decoding. We have seen the control unit. So how it is to be decoded. So the 3 bits will be given to the decoder, 3 to 8 decoder. So from the contents of that, processor identifies what is that instruction. As in the last section, we have seen like 000 represents one instruction, 0001 represents another instruction. Like that, from 000 to 110, we have seen different instructions, right? So in that way, like the instruction will be decoded. Then, if it is a memory reference instruction, reading the effective address from the memory if the instruction has an indirect address, or reading the operand directly if it is a direct addressing mode. So in that way, like for the memory reference instructions, we'll be performing a read operand also. Okay, or we can as well call as fetch operand. Fetch operand. So the next step is the executing. So executing the instruction. So in short, the instruction cycle consists of fetch an instruction, decode the instruction, fetch the operand, execute the instruction. Right? These are all said to be the steps, the sections of instruction cycle. Right? So after an instruction is executed, the cycle starts again with step 1. So as I said, like after instruction 1 is over, then again it has to start with instruction 2. The same thing, fetch, decode, fetch operand and execute. Fetch the instruction, decode, fetch the operand and execute. If it is not a memory reference instruction, it is simply fetch, decode and execute. Let us see what are all the sub-steps that happen during fetch and decode. I said like fetch is nothing but the memory read operation. Right, and it is an instruction. First step is instruction fetch. So instruction should be read from the memory. So where is the address of the next instruction available is program counter. So it is available in program counter always. So that should be transferred to address register during T0. T0 is the first clock cycle. So during that time, contents of program counter should be moved to the address register. So the selection of register is done by S0, S1, S2 as 0, 1, 0, which will be selecting the program counter, right? Then during the next cycle, next clock cycle, that is during T1, during the next time clock period, contents from the memory whose address is available in AR will be brought into IR. So these two together is nothing but fetching the instruction, right? And during decoding, what happens is, so only after fetch decoding should happen. So during T0, T1, fetching is done, fetch the instruction is done. So decode will be done during T2, and if required it may also extend to the consecutive timing signals, okay, time periods. So what happens during decoding is, so 12 to 13 bits, which are nothing but the opcode, will be generating the control signals D0 to D7. And the address part 0 to 11 bits, that is 12 bits, will be transferred to address register in order to fetch the operand from the memory. And whether it is a direct addressing or indirect addressing will be sent to I flag. This is a flag. I flag is used to represent whether it is using indirect addressing mode or direct addressing mode. So if it is 1, it is indirect addressing mode. If it is 0, it is direct addressing mode. So all these will be decoded. That is what is happening during T2. So this is nothing but decoding. Okay. Then if you look at the diagram, so what will happen is, so there is a common bus we have seen in the previous classes. There is a common bus, and which register is to be selected depends on, based on which register is involved in the instruction. Here we have seen like address register and program counter here. So appropriately the control those registers through S0, S1, S2 will be selected. And if it is memory read, see we have AR associated here, PC associated, IR associated. So first thing that happens is PC contents will be transferred to AR. So once they are done, then during next clock cycle, the contents from memory pointed by AR will be read into IR like this. Okay, it's a bidirectional bus, right? So that is fetch. And for decoding, what happens is, so IR will be given to the decoder unit. Okay. So different sections will be divided and will be going to the different registers. Address will go to AR register, I bit will go to the I flag, and 12, 13, 14 bits will be going to the decoder inputs. So this is how fetch and decode can be explained. Before execution, so while it is decoding, it will identify whether it is a memory reference instruction or register reference instruction or IO instruction. So how does the processor identifies is, one is the D7 bit is the one which determines whether an instruction is. So if you look at this, these two are for fetch and this is for decode. So after that execution should take place. If it requires any operand, that fetch should also happen. So for that it should identify first whether it is memory reference or non-memory reference. So if you see non-memory, I am saying as non-memory reference. Non-memory means nothing but register reference or IO instructions. Okay. So if D7 is 0, the meaning is that it is memory reference instruction. And again, if it is memory reference instruction, is it direct addressing or indirect addressing it is using to get the operand. So if it is direct addressing, during the next clock nothing will happen, time will be lapsed. Whereas if it is an indirect addressing, again memory fetch needs to be done. I mean that operand fetch needs to be done. So this part is for the indirect addressing part. So entire part is for the, this is for the operand fetch in case of memory reference instruction. So this is for direct and this is for indirect addressing. So after fetching the operand, then the memory reference instructions execution takes place during T4. Okay, this is the flow chart for executing. This part is for memory reference instructions. Then coming to the non-memory reference instructions, whether it is register or IO instruction. So which bit mentions that is that I bit. If I bit is 0, it is register reference instruction, right? And it will be executing the register reference instruction. I bit is 1, the meaning is that it is a input output instruction. Then it will be executing the input output instruction. So in that way, the processor will be identifying what is the type of instruction. Then what does the control unit do in order to generate the control signals? So appropriately as per the sub operations as we have seen. So the control signals that will be associated we can write, right? So whenever we are reading from memory, AR is fetching an operand into address register for indirect addressing. So that will be done. So this is with D7 0. So we include D7 bar so that D7 bar becomes 1. And during T3 this will be fetching. This will be performed. Right. So this is actually for this instruction, indirect memory reference instruction. This is the control signal that is generated. Whenever D7 is 0, the meaning is D7 bar is 1. Okay. So the meaning is it is a memory reference instruction. And if it is 1, it is a indirect memory reference instruction. So for this to happen, the control signal is this. For this, nothing should happen, right? So this is for there it is D3, D7 dash, I dash and T3 for this. So here I is 0. So I dash we include as a control signal and wired OR operation for this will be performed in order to generate the control signal. And for executing a register reference instruction, D7 is 1. So we include that as a control signal. And I dash for I dash because I is 0 for register reference instructions. And it is directly I for execution of input output instructions. So these are the control signals for execution of memory reference direct and indirect, register reference instruction and input output instructions. These are the 4 categories and the control signals that are required to be generated by the control unit when they are to be executed. So this is the complete flow diagram. So to see the register reference instructions, so this slide is showing how each of the instructions, what are all the register reference instructions? These, there will be like 12 instructions. Those 12 are from 0 to 11 bits, one at a time will be 1. So accordingly the code will be generated, right? And for all these instructions. So for all these instructions, the control signal that we seen earlier is nothing but D7 I dash T3 during execution. So that will be common. In addition to that, which instruction? So only one instruction should be selected. So for that purpose, that B0 bit, BI actually, BI bit is meant for, BI signal is meant for bits 0 to 11 of the address part of the IR register. Okay, it is address part. So whenever one bit is 1, that corresponding instruction will be executed. So it is associated with OR followed by BI. OR is the common control signal which we have seen just now for the execution of any register reference instruction. And each of the register reference instruction control signal is represented by BI. B0, if it is B0, the instruction is halt. If it is B1, it is skip if E is 0. Like that for all the instructions from 0 to 11. So with these control signals, these instructions will be executed. Okay, so this is sufficient, and what this slide is showing is what are all the sub operations that will happen, and the representation what it is showing is said to be RTL interpretation, which we'll discuss in another class. These are for the memory reference instructions. So the control signals that are for the memory reference instructions D0, D6 are the control signals associated with each of the instruction. Okay, D0 for the first instruction AND. Whenever we say AND, it is ANDing the contents of accumulator followed by the memory location it will be. So that content will be ANDed with the contents of the accumulator. For that, so the operand will be brought into DR, data register, and then data register and accumulator will be ANDed and result will be stored in accumulator. So during this time, the control signal, so up to this it will be performing fetching the operand, fetching the instruction, decoding, fetching the operand, and then execution. So execution part is this D0, T5, this will be performing the instruction. So same is the case with all the other instructions also. Add to accumulator, the next one is add. It will be followed with a memory address. That address is mentioning the operand with which the accumulator is to be added. So it will be fetching the operand from memory and then will be performing the addition with the data register and the accumulator. Any carry is there, that will go to the E flag, the carry bit. And after that, the sequence counter will be made 0. See, I said like after execution of every instruction, sequence counter is cleared in order to start a new instruction. Right? That is how this becomes a cycle. So same is the case, the remaining instructions. So in the same way, based on the operation, it is shown like what data transfers are showing for different instructions. This is also a memory reference instruction. I have explained 1 or 2 as an example. I am skipping these. So this is the entire flow chart, like what happens for first AND instruction, add instruction, load accumulator instruction, store accumulator instruction, like that. Okay, because I have spent some time for the instruction set, I'm skipping here. It is nothing like register transfers have been shown in the appropriate timing signal. The input output and interrupt instructions. So mostly the input output instructions are with the appropriate devices. The terminal with a keyboard and a printer, let us see in this, like, so a printer is connected to the processor as an output device and a keyboard is connected as an input device. So there will be an interface which will be transferring the type of data and speeds to the input register and giving to the CPU register accumulator. And when it performs certain operation and when it is to be displayed from accumulator, it will be taking the content to the output register and then to the interface and will be sent to the printer. Okay. So as we have already seen, these input output registers are of 8-bit register, and we have output flag and input flag, which is of single bit flip-flops. So which will be mentioning whether it is available, whether it is ready for inputting, ready for output, or enable input, enable output for that purpose. So thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.